All right, lesson 2.5, exponential function contests and data modeling. And so our skills and learning objectives for this lesson are we're going to construct a model for scenarios that involve proportional output values related to real world scenarios. We're going to apply exponential models about data sets in contextual scenarios. And we're going to construct exponential function models using regression equations and technology. All right, so in 5A, the exponential function context and data modeling, says there are many scenarios in the world that can be modeled by exponential functions. Some examples include radioactive decay, population growth, interest on savings, bacteria growth, and many other phenomena that occur in nature. So some real-world exponential models for population here. Example 1 says Surfside High School was built in 2007 and has a growth rate of 1.8% each year. The initial student population was A sub 0, which is equal to 1,483 students that year. The variable t equals 0 represents 2007 at the rate, and the rate r is written as a decimal. Write the exponential model A of t is equal to A sub 0 times 1 plus r raised to the t to represent the scenario. So we know it told us, remember, A of t is going to be our ending amount. We're just after the equation, though, here. R is going to be our rate as a decimal, so it was 1.8%, which is 0.018. It told us that A sub 0 is the 1,483, and then t is just the number of years, but when we're looking for the equation, since we have A of t is our ending amount, t is going to stay the variable. All right, so when I write my equation, I got A of t equals A sub 0 times 1. Now, they always put a plus here, but you need to think, is my thing that I'm talking about increasing or decreasing? If it's decreasing, you're going to be adding a negative number, which means you just put a minus there, okay? But here we have a growth rate. It's increasing, so of 0.018. raised to the t. And so we can simplify what's in the parentheses there. And there's our equation. Now B says to use your exponential model to find the expected student population in 2024. Now it did tell us here that t equals 0 represents 2007. So what will t be for 2024? Well, I'll take 2024 minus the 2007, and we get 17. So we know that t is going to equal 17. So A of 17 is equal to 1,483 times 1.018 raised to the 17. And so we put this in our calculator, and it gives us approximately 2,008 students. All right, then we talk about exponential growth and doubling time here. So the size of a population P at time t with the initial size P sub 0 and a doubling time of K is given by P of t is equal to P sub 0 times 2 raised to the t divided by k, where k and t are going to be measured in the same units of time. All right, so on here, remember that t is going to be your time, but k is going to be, it's the how long it's going to take to do what it's doing. In this case, we're doubling. So this is going to be the time needed to double. So how long does it take it to double? If that had been 3 raised to the t divided by k, it'd be how long it takes it to triple. If it had been 1/2 raised to the t divided by k, then it'd be how long it takes it to go in half the amount, or do the half-life. All right, so example 2 says a certain fish species was introduced into a tidal basin 10 months ago. The current fish population is estimated to be 220 and is doubling every 5 months. Find the initial size of the fish population. Well, that 220 we know is the population right now. All right. And let's see, we know that that population right now is at 10 months, so my T is going to be 10, and K is how long does it take it to double. It says, and is doubling every 5 months. So, using my equation here, my P of T equals, we don't know P sub 0, times 2 raised to the T divided by K. And so, we could take this 220 equals P sub 0 times 2 to the 2. Just 220 equals P sub 0 times 4 divided by the 4. And we find P sub 0, which is our initial population, the initial size of that fish population. And so we do the 220 divided by 4. And we get 55 fish. B says estimate the population of the fish 1 year after they are introduced into the tidal basin. So 1 year is 12 months because everything's been based on months here. So we're looking for P of 12. So I know my P sub 0 is 55 times the 2 raised to the T, which we said is 12, divided by K, which is 5. So I just type this into my calculator, and it tells me 290.292, and so we're looking at approximately 290 fish. All right, modeling radioactive decay. So suppose the half-life of a certain radioactive substance is 40 days, and there are 8 grams present initially. Find the time when there will be 1 gram of the substance remaining. And it gave us the equation there. It says we're going to say that A of T, which is our ending amount, is equal to A sub 0, the beginning amount, times 1 plus R, the rate as a decimal, raised to the T divided by K. Remember, T and K have to be in the same units of time. T is the time to find the ending amount. K is the time it's going to take to do whatever it's doing. All right, in this case, we're talking about the half-life. So K is how long is it going to take it to go in half. All right, so let's look at what they gave us. Suppose the half-life of a certain radioactive substance is 40 days. So there's my K. So my K is 40 days. And there are 8 grams present initially, so that's my initial amount. Find the time when there will be 1 gram, so that's my ending amount. And then I need to know, it says find the time, so we're after T, but what is R? Well, it's the half-life, so it's when it's going to be decreasing by 1/2. So R is going to be negative 1/2. So we have our A of T equals our initial amount times 1 minus the 1/2, the half-life, raised to the T divided by K, which is 40. And so I'm just going to clean this up a little bit. So that makes that a 1/2. Now, we haven't talked yet together on how to get T out of that exponent. All right, so we could start trying to get the 1/2 raised to the T divided by 40 by itself, but we had also talked about that we can take and we can put this side of the equation in y1, this side in y2 in our calculator, and we can find where they intersect. So let's do that. So in my calculator, in y1, I'm going to put 1. In y2, I'm going to put 8 times 1/2 raised to the x divided by 40. And I'm going to hit graph. And what I see here right now is the first thing I saw was a line go straight across. And then I saw another line doing something like this. Okay, not that close together on there, but you get the idea. So what I know is they're going to intersect somewhere over here. So I need to extend that x value, and so that's my x maximum. So I'm going to go to my window, and I'm going to change it to, 50. And I'm going to hit graph. So now I see that line. I still don't see the intersection, but I can see that they're getting closer together now. So I'm going to go and extend it again. I don't know, I'm going to try 500. And now I can see where those two actually intersect. So I see this, it's coming, whoops, it's coming down. And that's what I'm after right there. So I'm going to go to second, trace, intersect, hit enter 3 times. And it tells me that this point right here is at 120, 1. And so we want to know that x value, because that's what we put in for t. And so that's going to be at 120 days. So at 120 days, 1 gram remains. All right, example 4. Says the graph shown at the right contains the points -512 and 6, 1/2. Write an exponential function for the graph. Well, remember, an exponential function we talked about is y equals a times b to the x. And so with both of these, I know then that they give me an x and a y, so I can take that first ordered pair and write it into the equation. So I get y equals a times b to the -5, but we don't like negative exponents, so remember, we can send it to the bottom. Now we have a fraction. So this is 12 equals a over b to the +5. And then I could just solve that for a by multiplying both sides by b to the 5th. And so a would equal to 12 times b to the 5th. Now I'm going to do the same thing here to the second point. So I know that my y is 1/2 equals a times b to the x, which is 6. But I know what a is now because of this equation, the first equation. So I'm going to plug that in. So I have 1/2 equals a, which is 12b to the 5th, times b to the 6th. So 1/2 equals 12b to the 11th. Because when you multiply, you add the exponents. So now let's solve for b. So we can divide by 12. And then to get rid of the 11th as an exponent, we can take the 11th root, and we can actually do that in our calculators. So if you will type on your calculator 11, and then go to math, and you'll see the X root button. Choose it. It's number 5. And then you can just type in your 1/24 and hit enter. And it tells you 0.7490766,348. So we know that B is 0.749 approximately. And since you know B, now we can go backwards. We can take B and plug it in over here and solve for A. And so I'm going to write that here. So we said A was equal to 12B to the 5th. And so A is equal to 12 times 0.749 to the 5th. And I got 2.829. And so when we go to write our equation, we know our A, we know our B, so we can plug it in. And we get y equals 2.829 times B, so 0.749 raised to the x. And there's our equation. Part B says, what is the y-intercept of the function? Remember, at the y-intercept, x is equal to 0. So we're looking for when x is 0. So 2.829 times 0.749 raised to the 0. And so we work that out, and we get 2.829. So my y-intercept is going to be 0, 2.829. All right, and then example 5. It says a chemist has a 100-gram sample of radioactive substance. The table below The table below shows the amount of radioactive material at the end of the week for a 6-week period. A says use a graphing utility to fit an exponential function to the data and write the equation of the data. So we're going to go back and we're going to do that stat edit that we did before. So you're going to go to stat edit. And you're going to put this in. So you're going to put your weeks in L1 and your weight in L2. So pause the video if you need to do that. All right, once you get done with that, we just want to write the equation right now. So we can go to stat. We can go over to calc. And it told me it's an exponential function. So you're going to go, you're not going to pick linear. You're going to go find where it says exponential, which should be 0. Okay, exponential regression. So choose it. Our x's are in L1. Our y's are in L2. Don't worry about your frequency list. But remember the store regression equation? So before we went to vars over to y vars function y1, I did find to store it, if you will hit alpha, alpha trace, it gives us all of the y's there. And so if I want it in y1, I just pick number 1, which is y1, and it'll plug that in there. So I don't have to do all those other things to get there. Or you can do all the others, okay? So store it in y1 and then go to calculate. And so it should tell you then that y is equal to, remember we're going to put y hat because this is a predicted one. Okay, it tells you that A is 102.306, B is about 0.869, and it's y equals 80 times b to the x. So we can just write our equation. Y equals 102.306 times 0.869 raised to the x. And then B says, using your equation from part A, what value would represent half of the initial value? How many weeks to reach the half-life of the radioactivity? Does this correspond to the value, to the table of values? All right, so well, it wants half of the initial value. So my initial value is that 102.306. And if I want half of that, that would be approximately 51.153 grams. So I'm just going to multiply by 1/2 or divide it by 2. How many weeks does it take to reach that half-life then of the material, and does this correspond to the table of values? So if you look at it, 51 is closer to right here. So it does correspond at about 5 weeks in our table. So this value corresponds to about 5 weeks in our table. Then C says, when will there be 10 grams of material left? Well, that's my ending amount. So that's my y hat, my A of t, whatever you want to call it there. So we will say 10 is equal to the rest of that equation. All right, and again, we don't know how to get x out of the exponent. So I'm going to do y1, y2 intersect. So in my calculator, let me clear what's in mine out. So in y1, I'm going to put 10, and y2, I'm going to type in, well, you actually, you know what? Sorry, you already saved that equation when you ran that regression. So let's change this. This is in y1, so just go in your calculator and y2, put 10. Now I reset my window here, so I hit zoom 6, or I cleared it. I can see that my straight line, my Y2 is up at 10. So I'm going to go ahead and change my window. I want to move that window up, so that's my Y max. So move it up to, let's just say 20. So when I graph this, all I see is that 10. Well, think about the scenario here. We're talking about the base is 0.869, so we know it's decreasing. So what I'm thinking is, what we see right now is right here. I'm thinking this graph is going to come down like this because I know it's decreasing. That base is 0.869. And so I just need to go further out on my x's. So I'm going to increase my my x max. I'm just going to go ahead and put 100. Now I see my intersection. I'm going to go find it. So second, trace, intersect, enter, enter, enter. And I find that that point there is 16.561, comma 10. And so when will there be 10 grams left? At 16.561. And what was my units for time? It was in weeks. So we could say approximately 17 weeks. And how much radioactive material will be left after 52 weeks? Well, that is my x. X is my weeks. So I would just do my y hat equals 2.306 times 0.869 raised to the 52. And we can just type that in our calculator. And we should get 0.701 grams will be left. All right, and that is the end of part A.